Have you ever wondered how AI actually understands a story or translates a sentence, or even just follows a conversation? Well, that all comes down to one crucial thing: memory. It's about processing information in the right order. Today, we're going to unlock that very idea and dive into the world of recurrent neural networks, or, as we call them, RNNs.
But first, let's look at what happens when AI gets it spectacularly wrong. And get this is a real chatbot interaction. The user is clearly having a bad day, right? But the bot just latches onto the word exam and completely misses the point. It misses the emotion, the context. This right here is the exact problem we're going to unpack and solve.
So, why did that chatbot fail so badly? It's because most basic AI models just look at words in isolation. You know, they see the word exam, they see the word today, but they completely miss the story that's being told by the sequence of those words. The link between failed and don't feel like eating, it's just gone. It's missing that all-important context.
And this is where it gets really tricky for a machine. See, human language isn't just a jumble of words. It's this complex web of relationships. There are all these layers of meaning, right? The tone, the actual semantics, and sometimes a single word at the end of a sentence can flip the entire meaning of the beginning. It's an incredibly tough puzzle for an AI to solve.
So, to solve this puzzle, we need a totally different kind of tool. And that brings us to our first hero of the day, the recurrent neural network. Unlike the models that came before it, the RNN was built from the ground up for one specific job: handling data that comes in a sequence, like words in a sentence. And it does this by introducing the concept of memory. Okay, so check this out. On the left, you've got a standard network. It treats every single input like it's the first time it's ever seen anything. There's no past, no future. But the RNN on the right, it has that loop. And that simple-looking loop is an absolute game changer. It lets information from one step get passed on to the next. That loop is its memory.
Now, this memory has a technical name. It's called the hidden state. But honestly, the easiest way to think about it is just as the network's short-term memory. As it reads a sentence, word by word, that hidden state is constantly getting updated, carrying the context of what it just saw forward to the next word. So how does this actually play out? Well, let's take spotting names. Imagine the RNN sees the word Virat. It might be thinking, okay, Virat, got it. But because its hidden state, its memory, is holding on to that word, when it sees Kohli right after, it can connect the dots and say, aha, Virat Kohli, that's a name. That is memory in action.
But you know, like any good story, our hero isn't perfect. While this short-term memory is a huge leap forward, the simple RNN has a pretty critical flaw. And that flaw really starts to show when sentences start to get a little long.
So let me just ask you this. What happens when the context you need to understand the end of a sentence was mentioned, say, 20, 30, or even 50 words ago? Can that simple little memory loop really handle that kind of distance?
Turns out the answer is no. Not really. This is a famous issue called the vanishing gradient problem. And put simply, it means the AI's memory literally fades over time. The further back a piece of information is, the weaker its signal gets, making it almost impossible to connect words that are really far apart but still related.
Look at this example. It is perfect. To correctly pick between were and was, the AI has to remember the subject from the very beginning. But after that long phrase, with proper training, a simple RNN's memory can start to get fuzzy. It might forget whether the subject was men, which is plural, or man, which is singular.
So clearly, our hero needed an upgrade. The simple RNN hit a wall. And this challenge led researchers to develop some really clever, more advanced versions, like deep RNNs and bidirectional RNNs, designed specifically to beat this memory problem.
Okay, so first up, deep RNNs. Think of them like an onion of understanding. Instead of just one layer of processing, you stack several on top of each other. So the first layer might just get the basic words. The next layer up can start to see the relationships between those words. And a third layer could start detecting really complex stuff, like tone or even sarcasm. Each layer adds a whole new level of insight.
For instance, take this movie review. A simple, shallow RNN might just see the word boring and immediately think, okay, negative review. But a deep RNN, with all those layers, it has a much better shot at understanding the shift. It sees the but, it sees the amazing, and it gets the nuance that the overall feeling is actually positive.
But what about those sentences where the end changes the beginning? For that, we've got bidirectional RNNs. These are so cool. They literally read the sentence twice, once from start to finish, and then again from finish to start. This lets the network use context from the future to better understand the past. It's like knowing the end of a mystery novel helps you spot the clues at the beginning.
And this stuff isn't just a cool theory, it really works. Just look at the accuracy on a task like analyzing IMDb movie reviews. The bidirectional RNN gives a real measurable boost over the simple one. It's proof that looking both forwards and backward is absolutely crucial for true understanding.
Okay, so why did we go through this whole journey, from a simple loop to these complex two-way networks? Well, because these ideas aren't just history lessons. They are the absolute fundamental building blocks that today's giant AI models are built on.
So let's just quickly recap the breakthroughs. First, RNNs gave AI memory. Then, deep RNNs added layers of understanding, or depth. And finally, bidirectional RNNs taught the AI that context works both ways. And believe it or not, you interact with these foundational concepts every single day in things like machine translation, your phone speech recognition, or online sentiment analysis. And that brings us to a final, pretty mind-blowing thought. We've seen how each one of these innovations, memory, depth, and bidirectional context, solved a really specific problem. So if these are the foundational steps in AI's evolution, what even more powerful, more incredible principles are today's giant language models built upon? Thanks for joining me.